Okay, from this week, I wanted to talk about time series model. Okay, although we say something about the time series in chapter 9, okay, and I'm going to really talk about time series model, and which is not popular. It's really a popular, but for our IMBA program students, I think they are the first time to know the knowledge about time series model. So I wanted to introduce from very beginning. Okay, so some of your engineering students, maybe you all know much about it, but bear with us, okay? We need to do that for our business students, okay? And this is about chapter 12, okay? And so I will follow what in our textbook. And first of all, let's see, let's make it a little bit larger, okay? Then I'm going to use this one. Okay, then we can also see the PowerPoint, and I do some explanation. Okay, first of all, let's see the names, labels, okay? Distributed lag model. Look at this model, okay, which it pointed 7.14 means we already have that models in chapter 7. Maybe we not really pay attention to that, okay? But look at this model. What do you see the difference between this one and the one we usually have? The model, what's the difference? Also, what's unusual? In this model, actually, I have two x variables. One is x1, the other one is x2, right? Any other difference? First of all, it is the time series data. Therefore, we change the notation from I to T. Okay? So from now on, if you see the time series data, usually we put the T on it. Okay? And of course, we will put the I in it to identify as the different companies. Okay? So in that case, I do have different companies and also different years. And actually, if I have this I and T on it, I'm officially say this is not just time series data, but also cross-sectional data. In other words, it's the combination of time series data and sectional data. So in that case, we will call that panel data. Panel data, okay? This is a different data. Panel data with different cross-sectional data as well as time series data, okay? So we're not get to that yet. For in here, we don't have I, just have T. So I'm talking about one particular company or business or individual, maybe company is better, okay? And the T is identify the different periods only, okay? So this is a pure time series data with one company and different years, okay? Second one, what did you see the difference between this one with the original model we have? Here I do have x1 and x2, and x1 is the periods t minus 1. Do you see that? And x2 is t, and actually y is t. So in other words, before we are talking about the relationship between the current period, current times, no matter it is x variables or y variables. But now, if we have the time series data models like this one, okay, this is called distributed lag model. Okay, so means lag independent variables can be used when X is expected to impact Y after a period of time. Okay, so this is called simple lag. And do you think OLS, so far we learned OLS estimation, right? So OLS can do this one? Say yes, OLS can estimate without any additional complications. Okay? And this is the simple one, simple lag. Okay? More complicated case is when an independent variable's impact is expected to spread out over a number of time periods. So in other words, not only t minus 1, I may have more periods like t minus 1, t minus 2, t minus 3, t minus 4, etc. Okay? And we call this one is distributed lag model. Okay? Then, so like this one. So a distributed lag model explains the current value of Y as a function of current and the past the value of X. All right, so for example, you can see 12.1 or 12.2. So 12.1, we have t minus 1, t minus 2 for one particular variable, X, which is t minus 1, and t minus 2. Okay? Then a more general distributed lag model is the one not only with t1, t minus 1, t minus 2, may be extended to previous p periods. Okay? So this is 12.2. So p is the maximum number of periods X is lagged. Can you think about the example that the current YT will affected by the previous, the current as well as the previous X variable? Cells. Okay, the current cells will be affected by the current advertisement as well as the previous advertisement. So in other words, the advertisement, the effect of the advertisement is not just only the current periods, but also in the future. So if I have some cells, this periods, it may be influenced by the previous advertisement. Okay? Anything else? Foreign exchange. Okay? Anything else? You all in emphasize in research. Okay? In the business area, they have do some research. Okay? So like TSMC, they do a lot of research, right? So they put more money on the research. And what all this research will affect the cells in the future, right? And the study shows that all the research, did I put this one? I'll put it back. Okay, all the research will affect after 4 years. So in other words, if I have the Y, which is the cells, then X is the research expenditures. Then my X variables should start with X t minus 4. Means that whatever I put on the research expenditures will not affect current or next periods. But after 4 years. This is according to the research result. Okay? Therefore, if you, the many companies is really, if they don't have the future perspective, then they're really, don't like to put much research expenditures because the effect is after 4 years. Okay? But if they have, is a well-established company and they have long perspective, then they should put a lot of research expenditures in order to increase the sales. That is why TSMC is so, the business so well. Okay? All right. So this is what we say, distributed lag model means the current Y will be affected by the several periods of X. Okay? All right. Then let's see. If I use OL as to estimate distributed lag model, there are many kinds of problems. Okay, so let's think about it before we see the answers. Okay, let's think about according to what you have learned so far. Then can you think about if I use OL's methods, what happened? What kind of problems I will have? Although we can use OLS, but still we have some problems with it. So can you think about what kind of problems? Think about this is sales, and this is advertisements. This is all X, but different periods, previous years, previous 2 years, previous 3 years. What do you what you have learned so far? You have the knowledge to explain this question so far. What is it? Think about it. Anyone? Nothing? Nothing on your head? Nothing on your mind? So what do we learn from the beginning of this semester? What topic do we learn? The first one, we are talking about multicollinearity, right? The second, we talk about heteroscedasticities. We just talk about 2 issues only so far. Then we started to talk about time series data. Okay? What's these 2 knowledges? Can you explain these questions? What is this? What is this one, this one, this one? Any idea? If you see our X variables, it's like this one, this one, this one, this one. What I'm trying to say is, when we say the OLS model, we wanted to have all the X variables. What? The relationship between X variable is the correlation is as small as possible, right? So we call them, the best way is independent. Okay? So now I'm asking you, this one, this one, this one, and this one. Are they related? Are they related? This one, thinking about expenditures, right? Current, previous to. If the companies decided to, we have some advertisement, okay, how do they decide the advertisement? They base on the past experience to see how much I put on the advertisement, then I will increase my sales. Okay? So is there any relationship between, between those experiences? How come there's no pointer? Oh, here. This one. So actually, xt minus 1, xt minus 2, they're related, right? And what kind of problems do we have if I use the OLS model? Estimation. Multicollinearity problem, isn't it? Right? Multicollinearity problems. Okay? You know? So let's see. This is a big problem. The biggest problems from the models, from the model itself. Okay? So let's see. The first problems, various legs of x are likely to be severely multicollinear. Okay, so you understand this one, right? Okay, before we see the answer, after we have some thinking, then we see the problems that train ourselves to think of the problems. Okay, then the second one. There is no guarantee that the estimated beta will follow the smoothly declining pattern theory would suggest. What does that mean? Go back to the sales and expenditures, okay? Means that the current expenditures may have directly effect on the sales at the same time periods, but the previous one do affect the current sales. But the longer the advertisement, the before, right? The previous period, the less the effect on the current sales, isn't it? Right? Understand what I'm saying here? So this is, I'm saying that there is no guarantee. That means all this beta coefficient here, all this beta coefficient, since this is t minus 1, t minus 2. So this beta, I think we have the positive relationship between the advertisement and sales. So maybe here shows the beta 0 is the big effect. Then beta 1 will be smaller than beta 0, all positive. Then beta 2 is even smaller than this one, isn't it? This means that all these periods, after the extension of the past periods, will less effect for the current sales. So we are expecting all this beta is positive, but the number of the beta we estimate using OLS is getting less and less. This is what we're saying, right? Agree with us? So this is what we're saying. But it shows that the problem is there's no guarantee that estimated beta will follow the smoothly declining pattern theory would suggest. Okay, we're going to use the data to show the problems. Okay, later on, okay? All right? 3, the degrees of freedom tend to decrease for 2 reasons. First one, each lag x has a coefficient to estimate. Each lag x decreases the sample size by 1. What does that mean? The more periods, previous periods, the more x variables I should put on my model. Therefore, there are more estimation. And when we say degrees of freedom in regression analysis is n minus k minus 1. N is the sample size. K is the number of x variables. Then minus 1 is the intercept. All right? So the more for the previous periods, the less degrees of freedom. This is what the problem say. Okay, let's go back to see what's the problem say. The degrees of freedom tend to decrease, right? The more past periods, then that subtract more x, the number of x variables. So the degrees of freedom tend to decrease for two reasons. One is lag x as a coefficient to estimate, and each x decreases the sample size by 1. This is what this 2 explained. Anything else? Let's see. Okay? All right? So this is what we introduced for distributed lag model. Understand it? Or understand it? Okay? All right. Then there's another type. This is the first type. Okay, we're going to introduce 2 types. Okay, so let's go on. This is another model. It's called dynamic models. And the simplest dynamic model is like 12.3 equation. So what is it? It is the 1x variables. And the other one is what? Yt minus 1. This is what we call lagged dependent variable. Okay? This distributed lag model is what we say lagged independent variable. You see the difference? Lagged independent variable is what we call distributed lag model. Okay? And dynamic model is the lagged dependent variable. That's the difference. And interesting, with some math or algebra, okay? I think I should say algebra. It's not really advanced math. Okay, some algebra. 12.3 can be used to represent distributed lag model. In other words, 12.4, 12.3 can be extended, okay, into, not extended, can be equivalent to distributed lag model. Okay, if you don't believe it, then see how do we do it. Okay, this is a little bit algebra only. Okay, so let's see. Look at 12.4. It is from 12.3, but previous periods. So the yt if I choose t, becomes t minus 1. So I put every t. Then t minus 1 becomes t minus 2. And this t is t minus 1. And this ut is ut minus 1. But, here, I have to say that. What's the assumption of this ut? Ut is the arrow terms, right? UT is the arrow term, right? Whatever I say the distributed lag model, let me go back. The expression of 12.1 or 12.2, okay? The assumption of the arrow terms. The arrow terms of this one should be IID. You know what's the IID means? Identically, individually identically IID distributed. Means follow the assumption of OLS estimation. So in other words, this one is what we call white noise. Okay? This is the white noise. Therefore, if I have several X variables here, I can use OLS model because it just follow the assumption of the OLS estimation. Understand what I'm saying here? Okay? So same as the dynamic model, the UT here is also white noise. Okay? It's the white noise. Okay? Let's see. Look at 12.4 is one lag previous periods of the 12.3. So if so you should have no problem with this one and this one, right? Okay, now substitute equation 12.4 into equation 12.3. Okay, so here I have the 12.3. That's my pointer. I don't. What's wrong with this one? I thought, I'm too short. I cannot always point it to that area. So I should use the pointer to help me. Now, this pointer is not that sensitive. So I'm not able to point it. Oh, here, okay. Look at this one. Substitute 12.4 into 12.3. So look at the 12.4 with yt minus 1. So I subtract everything into the yt minus 1. You understand what I'm saying here? Then it turned out to be 12.5. Look at this one. So look at, since I'm using 12.4, plug all this yt minus 1 into 12.3. So my 12.3 becomes to, this one is the same as this one. And t is the same as this one, but I will replace these parts with everything up here. Did you see that? Understand what I'm saying here? Okay, so since I plug everything into these parts, that's why I have the everything here, then plus the ut. Okay? All right? So let's go on. Okay, then I do some combination, okay, with the same variables and put them together. Okay, so I do have, I can rearrange it to equation 12.6. Okay, so it becomes that, and I really arrange it. Then I'll see it turns out to be 12.7. Okay, in other words, from 12.3, which is the simplest dynamic model, 12.3 can be expressed as 12.7, which is the expression. And do you see the difference between 12.3 and 12.7? see it again for 12.3, is the current xt with the previous t minus 1, and 12.7 is the one with current t and the t minus 1, t minus 2, then this one. Then you can see that after I do several times, then t minus 3 can be also expressed as xt minus 3. You see the points here? In other words, dynamic model can be expressed as a distributed lag model. Okay? Although we say it is dynamic model, but it can be expressed as a distributed lag model. All right? Okay? Is that clear? For my business students, I do some of the simple linear algebra only. Okay, so do not worry about, this is not really math. It is elementary math. Elementary school math. Okay? You understand? The older expression is trying to say that although we say time series do have what we call the dynamic model, but it can express this as the distributed lag model. And why do we want to express the dynamic model into the distributed lag model? Although the distributed lag model, we just say that they do have several. If I use the OLS model, I do have several problems. Although I have that problems, but I still wanted to express the dynamic model into the distributed lag model, because although distributed lag model can be, use the OLS estimation, can cause several problems, but still later on, you can see that there's some advantages. There's some advantages, although they do have multicollinearity problems. Okay? All right? So now, let's using the examples to show what I just say. Okay? All right? Let's see. Okay, continue. Okay, I think we haven't finished all this dynamic model yet. This previous one is just only extended to 2 periods. I do have a lot of t minus 3, so I can also continue extended this one. Okay, so this can be extended to 12.8. Okay, and you can see that if I extend it from if I extended my dynamic model into the distributed lag model, the relationship between these two can be look like this way. Let's see. So in other words, is this beta 1, beta 2, beta 3 can be the beautiful relationship. Look at this one. So you understand what I'm saying here? Let me see the previous one. Okay, this 12.3 is what I started with, which is dynamic model. So 12.3 can be expressed as a distributed lag model, then all can be, and all the coefficients like this. Okay? It is clear? Let me think about it. Okay? This is the example we're going to show. Let me write down it here. Maybe it's more clear, okay? Let me write down it here. In other words, if I have the y equal to, this is alpha 0, this is the intercept, okay? And they started with beta 1, beta 0 is x. Okay, I'll put this t here, okay? T. And if I have the beta 1, like this one, okay, this is, I'm using the example, lambda yt minus 1, right? Plus ut. So this is 12.3. This one can be expressed. This is what we call dynamic model. And this one can express it as a distributed lag model, which means that yt equal to alpha 0 plus beta 0 xt. Then if it is the distributed lag model, I should have xt minus 1, right? Then plus, and I put this coefficient later on. Okay, then xt minus 2 plus plus xt minus p, okay? Then plus the original ut, okay? And what are these coefficients? This means I'm using red one, okay? This means what? If I see this one, this is what I say. Isn't this is beta 1? So this should be lambda, no ink. Okay, this one. Okay, lambda, beta 0. Do you see that? Then the beta 2, this is beta 2, is lambda square beta 0. Isn't that beautiful? So you can see the relationship from the dynamic model into the lag, distributed lag model. So this one, this lambda square is followed by the lag. Do you see that? So minus 1 is 1. Minus 2 is 2. So this one up to minus p, it will be lambda p beta 0. So this is by theoretically. Okay? By simple linear algebra. So express the relationship between the dynamic model into the distributed lag model. So now I'm going to use one example to show if I have exactly the data, do I have all this result? Okay? All right? Okay? By the way, before we get to the data, do we see that all this one, since this is the coefficient to the lag of x to the effect to the yt, so theoretically this beta should be decrease because I'm saying that if this is xt is the advertisement and this yt is the sales, right? So the current advertisement will beta 0 affect yt, right? But this one is the previous advertisement. And according to real situation, the previous periods will less effect than the current sales. So theoretically, this one is smaller than this one. Okay? All right? So let's see let's see this one. So as long as the lambda 0 to 1 is between 0 to 1, then the numbers of this one will smoothly decline. This is what we're saying. The coefficient smoothly decline. Okay? All right? Any questions so far? Do I make it clear? Understand this one? So this is all theory, according to the theory. Right? All right. Then now, let's use the example. All right? Let me see. What example? And yeah, okay. Okay. This is some relationship if, since alpha should be 0 and 1. So if alpha is 0.02 and alpha is 0.5 and alpha is using 0.75, they're using 3 different numbers. One is in the middle, the other one is pretty close to 0, the other one is close to 1. Okay? What did you see the relationship? So we say that as long as lambda as long as the lambda between 0 and 1, a dynamic model has impact of the independent variables declining as the length of the lag increase. So declining. But if the lambda is bigger, then the speed of the declining is what? Is slower. If lambda is small, where is it? Lambda is smaller, it's decline fast. Okay, since I have to square it, right? If the small number, I square it even smaller. All right? Okay. So far, I think we understand this one, right? Okay. Then let's use in the example, which is I'll see this one, okay? The example is, I have the data. Okay, which one? COYD. Okay, this is, okay, if you go to the iLearnings, and we do have the data, which is called macro 14. So in chapter 14, okay? I'll download that data. I'll go to the data, okay? I'm go to the iLearning, okay? Go to the iLearning. Go to chapter 14, okay? and I'll use the eViews. And did you see that? Macro 14. Okay, macro 14. Okay, I'll download this one. Okay. Okay, let me. Okay, I have this one. All right. In order to know the data more clearly, I also download my Excel. Okay, this is exactly the same. You just want to see the numbers. That's it. Okay, because Excel is more easier to do the original data, from my point of view. Okay, eViews is hard to see that. Okay, so let's see the data set here. Okay, how many observations do I have? This is year from 1975 to 2007. So is 33 years, right? I have 33 years. And the first year is consumption, and the first year is only data consumption, and the rest of the data is started with the second year. Okay, so I do have, so you know that since this is we started with 75, so actually CO, we do have T minus 1. You see? You understand what I'm saying here? Then, so let's see, what's the X variables, what's the Y variables? Okay, so look at, if you have the textbook, let's look at, this is an example of the dynamic model, which is on 12.4. Okay, I'll see that. Okay, this is, so we see the examples, right? And CO is my Y variables, and YD as well. YD is my X variable. Okay, CO is Y variable, and YD is X variable. All right, so let's see here. Then I'm gonna get out of here. I'll go back to my PowerPoint. Okay. Okay, so let's see this example. So CO is my Y variable. YD is my X variable. And I do have YT minus 1, T minus 2, etc. Okay? All right, so this is what we call what model? What's the 12.9? What kind of model is this one? What kind of model is 12.9? Distributed lag model, right? Okay, and since we know that 12.9 is distributed lag model, it can be expressed as dynamic model, didn't we? So most econometric model equation 12.9 with a dynamic model is like this one. Okay, so 12.10, actually 12.10 and 12.9 is the same. Okay, so 12.10 is using CO as a Y variable, and YD, current YD is X, then the lagged YD. Okay, did you see that? Okay, understand this one? So I like to estimate the data using these two models. Okay? Okay, let's have a break, 10 minutes break, okay?